Hello everyone! In this video, we're going to learn how to find the derivatives of functions using the limit process, or the definition of the derivative we derived last video. Okay, so what we're going to do is we're going to first find the derivative of a relatively easy function. Have f of x equal to 2x. What is f prime of x? F prime of x is the derivative of f of x. That's how you write the derivative of f of x, f prime of x. So f of x equals 2 times x. Well, the derivative, f prime of x, equals to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, so what can we do here? Well, first let's just substitute the actual function in here. So the limit, this equals a limit as delta x approaches 0 of 2 times x plus delta x. Remember, we're just evaluating the function for the top, for a numerator, at x plus delta x and at x. So all that over delta x. Now we're going to distribute the first expression, the first term, in the numerator. So we're now going to have the limit as delta x approaches 0. So let's just quickly distribute 2x plus 2 delta x minus 2x over delta x. So these two cancel, and with the resulting division, the delta x's also cancel. So we have a limit of a constant. We have the limit of a constant. So that will just be equal to 2. And this result sort of makes sense, because if you imagine what the graph of f of x would look like, what the graph with f would look like, it's a line. It's a linear equation with slope 2. So since the derivative is at the slope of a point, the slope of at every point of f will always be 2. 2 is the slope of the entire line. Lines have a constant slope, as shown here. However, there are lots of functions which don't have a constant slope. Let's do an example of that right now. So let's make f of x equals x squared. So if you have graphed a quadratic like this before, you have to know that it's a curve, it's a parabola. So it doesn't have a constant slope, which means we should not get a constant value, but let's just see. So we're going to find f prime of x using the limit definition. The limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, so how are we going to tackle this one? First, we're going to evaluate the function for the numerator. For the terms in the numerator, let's evaluate the function. So we have x plus delta x squared minus x squared over delta x. So what I'm going to do now is we're going to expand the squares, the squared binomial at the top. So you can use the formula, which you probably remember from algebra, a squared plus 2ab plus b squared. So let's apply that same formula to the top. Okay? So that gives us a squared plus 2, so x squared plus 2x delta x plus delta x squared minus x squared. All that over delta x. So these two subtract out, and so we get the limit as delta x approaches 0 of 2x delta x plus delta x squared, all that over delta x. So what we want to do is get rid of the delta x in the denominator, so we don't get a 0 in the denominator, okay? So what we're going to do is factor out the delta x in the numerator. Okay, since there's delta x, at least one of them, in both terms. And using the factored expression, look what we can do now. Cancel, cancel. So we have the limit as delta x approaches 0 of 2x delta x, which is a lot more manageable, in my opinion, because we just substitute in 0, we get 2x. So the slope is not constant, okay? At every x value, there'll be a different slope, which makes sense, okay, intuitively. Since x squared will have a positive slope above 0. It will keep on increasing, and will have a negative slope when x is less than 0, just like f prime of x. F prime of x will be negative, okay? Now, if you're clever, you could have done this in a much easier way, I believe. Okay? So you could see that this is actually a difference of squares. Okay, so here's the alternate way. I'm going to use a different color. So this is a difference of squares. So you could do a plus b, a minus b. And that gives us, well, 2x plus delta x, 2x plus delta x times, well, these two cancel, we get delta x. So we don't even need to do all the expansion and factoring business, since we just got the same result as here. Okay, cancel, cancel. So now if you are clever, you're going to just skip to this step using difference of squares, and this would lead to here and lead to here, our answer. Okay, so there's more than one way to approach these. However, for some functions, well, there's really only one way to do it. Okay, so let's look at our next function. What is, let's go to my signature black color again, f of x will now equal 1 over x. Okay, 1 over x. So we want to find f prime of x, the derivative of 1 over x. Well, we can just use the limit definition just as we have been doing this entire time. F of x plus delta x minus f of x over delta x. So what we're going to do now is evaluate the function for the numerator, for each term in the numerator. So you have 1 over x plus delta x minus 1 over x over delta x. So let's combine these two fractions in the top. So we have x minus x plus delta x. If you were to use a like denominator, we have x times x plus delta x. All of that over delta x. Cancel, cancel. Good. So what we now have is, you might be noticing I'm not putting limit. It's a bit of a pain, but we have to remember, at the very last expression, you should put the limit. It is still a limit, so I can neglect it for now. Okay, it's a convenience. So what we can do now is rewrite this as negative delta x. Remember that negative distributes, goes over, times x plus delta x, all that over delta x. Or another way of writing it is negative delta x over x times x plus delta x, tons of delta x's, of course, times 1 over delta x. And I wrote this way because now I can easily see it cancel, cancel. And now we have the limit. Remember, we still have to put the limit statement. Okay, it's just been omitting it for convenience. Of negative 1 over x squared plus x delta x. And now this doesn't make the denominator equal to 0, so we're in luck. We are in luck. So if you do direct substitution and evaluate the limit, you get negative 1 over x squared. Negative 1 over x squared. And that is our derivative. There's a final type of function that you can use this for, although it's even trickier than all of these. The radical function. So let's have f of x equal the square root of x. Okay? Now, f of x equals the square root of x. To find a derivative f prime of x, well, we just take the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, it was the same thing as the limit as delta x approaches 0 of the square root of x plus delta x minus the square root of x over delta x. Now there's really only one way to go about with this. We have to rationalize the numerator. So we can do stuff to the denominator, which will eventually remove this nasty delta x in the bottom. Okay, so let's rationalize the numerator. And to rationalize, you simply multiply it by its what I call an opposite. So that you create like a difference of squares product on the top. That's the key of rationalization. They remove the radical on the top and basically shift it to the bottom. Okay? So, now it seems like we made the limit a lot worse. Seems like we made the limit a whole lot worse. X plus delta x minus x over delta x times the square root of x plus delta x plus delta x. So it looks a whole lot worse, but if you notice, cancel, cancel. You just subtract, and now we only have a delta x on the top, we have a delta x on the bottom, cancel, cancel. Which means you can now evaluate our limit. We don't have that delta x on the bottom becoming 0 and ruining everything. So we have 1 over square root of x plus delta x plus square root of x. If through direct evaluation, you get 1 over the square root of x plus square root of x, or 1 over 2 square roots of x. So you could do these for any of the functions that even remotely look like this. However, if you really want to find derivatives of polynomial functions and more complex rational functions, then this is not going to work. You can see how tough this is already for basic functions, like just a basic square root function. For real polynomial functions, it'll be a whole lot worse, which is why we're going to learn a bunch of easy tricks and rules to help shorten this process in the next video.